Let me share the screen. You're able to see my screen?
Yes, sir.
Okay, great. So, in yesterday's class, we have looked at the various failure theories, and we said we've actually looked at the first three failure theories, that is maximum normal stress theory, maximum normal strain theory, and total strain energy theory. However, we also argued that these three theories, they do not match with the experimental data. And as a result, two new theories have come in. They are called distortion energy theory or von Mises-Sankey theory or maximum shear stress theory or Tresca-Gas theory. These two theories are most popular because they match with the experimental observations very closely. And we'll see why, what is the genesis of these theories. So let's look at the distortion energy theory. What this distortion energy theory says is the following. Before we understand what distortion energy theory says, we would like to look at what is the physical meaning of plastic deformation or onset of yielding. So microscopically, the yielding, that means the onset of plastic deformation, is due to relative sliding of atoms within their lattice structure. We have studied dislocations, and plastic deformation is nothing but the onset of plastic deformation is nothing but onset of dislocation motion. So how do dislocations move? When the dislocations are subjected to macroscopic shear locally, these atom planes shear past each other, and that is what is we see it as plastic deformation, right? So this sliding of atom planes is caused by shear stress, which is also called dislocation motion. And as a result, what happens is your lattice will get distorted. That means lattice will change the shape. So now, whatever energy that you are putting in, suppose if you are applying a load on a material, then you are putting in some energy, deforming a material. The energy stored in the material will have two components. What the energy contributed to the distortion, meaning shape change of the material, is an indicator of shear stress present. So in earlier, what people were thinking was the total strain energy stored in the material causes yield failure. That means causes the onset of plastic deformation. Total strain energy means area under the stress strain curve up to the yield point. This is the total strain energy. People who thought that this total strain energy, when it is becoming equal to the strain energy, it becomes equal to the yield strain energy, like in the case of total strain energy theory. That is when failure happens, was the old school of thought. But again, the experiments have proved them wrong. That means it is not the total strain energy that is responsible for plastic deformation. So now let us look at it. So the total strain energy density is 1/2 sigma times epsilon if you are assuming a uniaxial state of stress. But if you are talking about a three-dimensional state of stress, you have sigma 1 epsilon 1, sigma 2 epsilon 2, sigma 3 epsilon 3. This is something that we have seen in the yesterday's class. And we have constitutive relations. Strain and stresses are related to Young's modulus and Poisson's ratio like this. These are principal stresses and principal strains. And now you plug in epsilon 1, epsilon 2, epsilon 3 with these expressions, then the total strain energy density is equal to 1 over 2E times this. This is something that we have derived in yesterday's class. What old school of thought was, when this energy in a material becomes equal to the total strain energy at the onset of yielding. That means 1/2 sigma y times epsilon y. When this becomes equal to 1/2 sigma y times epsilon y of that particular material, that is when yielding happens. Right? But people later thought the data proved them wrong. Then there were some experiments done by this guy called Bridgman. What he said was the following. Whenever you deform a material hydrostatically. What do you mean by hydrostatically? Apply the same stress in all the 3 coordinate directions, right? Then what happens is the material will not change its shape, but it will change its volume. Let us say you are compressing, hydrostatic compression. That means in all 3 directions you are applying the same stress. Then a sphere remains sphere. It will not change its shape, but it changes its volume. Okay. That happens. So a very large amount of energy can be stored in a material without failure. Failure here means distortion, shape change. But when you apply same stress in all the 3 directions, there will not be any shape change. That means there is no distortion. Whenever we are talking about plastic deformation, we are talking about distortion. But when you are applying a hydrostatic state of loading, you are not causing distortion. It means you are not causing shape change, but you are only causing size change or volume change. So what Bridgman did was, he did a very interesting experiment where he subjected ice to 1 megapounds per square inch hydrostatic compression, and it did not fail. It is huge hydrostatic pressure. So the hypothesis is, if you are applying uniform stress in all 3 directions, that means if it is hydrostatic state of stress, only volume changes, there will be no distortion. So if you have a hydrostatic state of stress, and if you draw a Morse circle, what do you mean by hydrostatic state of stress? Sigma 1 is equal to sigma 2 is equal to sigma 3. All right. When we have drawn the Morse circle earlier, if you are talking about Morse circle for a 3D state of stress, this is sigma 1, sigma 2, sigma 3. Then this is how the Morse circle for 3D state of stress looks like, and the green area is the valid states of stress. Now, if you imagine a scenario, sigma 1 is equal to sigma 2 is equal to sigma 3, then all these circles will boil down to a point. Then the Morse circle will be a point that on normal stress axis. That means, for example, if you take this state of stress, what is the idea of Morse circle? Even if you are applying along this plane, if you are applying only uniaxial state of stress, there are planes at which you will still experience shear stress. A plane oriented at an angle 2 theta from the original angle axis will have experience some shear stress for an angle. So for example, this is at an angle from this state of stress, it is at an angle 2 theta P1. So that means, although on this plane you have only normal stresses, there is a plane oriented at an angle 2 theta P1, there you will have normal as well as shear stresses. That means even if you are applying uniaxial state of tension here, you will have planes at which you will have some shear stress. And there will be one plane at which you will have maximum shear stress, which will be at an angle 2 theta 90 degrees, that means theta 45 degrees. So that means if you have, this is your principal stress plane, a plane oriented at an angle 45 degrees to this principal stress plane will have maximum shear stress. But if you have hydrostatic state of stress, sigma 1 is equal to sigma 2 is equal to sigma 3, then you will have a point, because the circle with 0 radius, that means there will be a point, will be a Morse circle, which means there is no plane that experiences shear. If there is no plane in the material that is experiencing shear, then there is no shape change. So that is the idea of this concept of hydrostatic stress. So now, the total energy that you are giving to a material can now be divided into, total strain energy can be divided into 2 parts. A part of it is spent for shape change, which is called hydrostatic energy. And a part of it is, used for volume change, that is what is called hydrostatic energy. And a part of it will be used for shape change, that is what we call distortion energy. So the total strain energy in the material can be decomposed into 2 parts, UH plus UD. Okay. Now you have sigma 1, sigma 2, sigma 3 are your principal stresses. Again, the stresses can be divided into 2 parts. One is hydrostatic part and a deviatoric part. So because we are saying hydrostatic part should be same in all the 3 directions. So sigma H, sigma H. So sigma 1 can be written as sigma H plus sigma 1D. That means this is the deviatoric part, which is purely responsible for shape change. this is purely responsible for volume change, size change. If you add all of them, sigma 1 plus sigma 2 plus sigma 3 is equal to 3 sigma h and this one. So 3 sigma h is this. If you have a scenario where there is no distortion at all, that means this component should become 0. Then the hydrostatic state of stress sigma h will be equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Because under pure volume change, there is no distortion. So this component will become 0. Then your hydrostatic stress, if you have sigma 1, sigma 2, sigma 3 as your principal stresses, then the hydrostatic part of the stress will be sigma 1 plus sigma 2 plus sigma 3 by 3. Okay. So the hydrostatic stress will be same in all the three directions. That is sigma 1 plus sigma 2 plus sigma 3 by 3. If your stress, the three principal stresses are sigma 1, sigma 2, sigma 3. If all of them are same for a hydrostatic part, so UH will become sigma h square plus sigma h square plus sigma h square minus 2 nu sigma h square, sigma h square, sigma h square. So that will be 3, 6 nu sigma h square, right? If you plug that all that in, then you can 3 nu c sigma h square and 3 by 2, 1 minus 2 nu by e sigma h square, and sigma h is equal to sigma 1 plus sigma 2 plus sigma 3 by 3. So the hydrostatic part of the energy, strain energy, will be this much. And we have already computed total strain energy. And the total strain energy is sum of hydrostatic plus distortion energy. Now we have computed only the hydrostatic part. So now the distortion energy will be total strain energy minus hydrostatic part, and that will be this. And if you do algebra, this is how it looks like. 1 plus nu by 3 times sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 sigma 2 sigma 3 sigma 1 sigma 3. This is the distortion energy, and this is the of the total energy that you have supplied. Only this much energy will be used for shape change. So in a uniaxial tension test, what are your sigma 1, sigma 2, sigma 3? Sigma 1 is equal to, at the onset of yielding, sigma 1 will become equal to sigma y. Sigma 2 and sigma 3 are 0. So when you plug that in, so distortion energy at yielding for a uniaxial tension test, then that will be 1 plus mu by 3 is sigma y square. So when will a material which is subjected to a three-dimensional state of loading will plastically deform? When this energy becomes equal to this energy, that is when it plastically deforms. Or it is safe as long as UD is less than UDY. So failure criterion is UD is less than UDY, and you plug that in. So this is the condition. When this value is less than sigma y, then the material is safe. That means the material is under elastic state. It is not plastically deforming. The moment it is equal to sigma y, that is when it plastically deforms. Okay. So this is what we call distortion energy theory. The statement of distortion energy theory is this: square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 should be less than sigma y for material to be safe. So now this entire quantity can be given a name called equivalent stress, sigma E, or it is also called von Mises stress. When this quantity, that is sigma E or sigma Vm, is less than sigma y, then failure does not occur. Then the material will not be plastically deforming. But when this becomes equal to sigma y, that is when material plastically deforms. And that is precisely the reason why, if some of you are doing finite element analysis in some finite element software, you always compute von Mises stress or equivalent stress. And that stress, if it is equal to sigma y, then you say that the material is plastically deforming. And that is coming from this distortion energy theory. And from this, you can generate special cases. If you have a material which is subjected to pure shear. What do you mean by pure shear? Pure shear means sigma 1 is equal to minus sigma 3 and sigma 2 is equal to 0. If you plug that in, sigma 1 is equal to minus sigma 3, that is equal to tau, the applied shear torsion of the circular shaft, and sigma 2 equal to 0. Then under pure shear, sigma y square is equal to sigma. This is the condition for failure. So that means 3 tau max square or 3 sigma 1 square or sigma 1 is equal to sigma y by root 3. So that means when the principal stress becomes 57.7% of yield strength of the material, that is when failure happens, or when the maximum shear stress is equal to 0.577 times sigma y, that is when failure happens. When the loading is pure shear. Okay. So now let us look at this scenario. This way. If you look at this fellow, what is the load that is applied? Sigma. Uniaxial tension test. Let us now use our formula. Please note down the formula, that is square root of our condition for failure is this. Sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1 should be equal to sigma y. That is the condition for failure. If it is a uniaxial loading, to sigma 2 is 0, sigma 3 is 0. So this one will be 0. So square root of sigma 1 square is equal to sigma y, or sigma 1 is equal to sigma y. That means the failure happens when sigma 1 is equal to sigma y. When the applied sigma becomes equal to sigma y, that is when the failure happens. You can see that. Now here what you have? Sigma 1 is equal to minus sigma, sigma 2 is equal to plus sigma. If you plug that in, can you please do that in the, take a pen and paper? In that equation, you want me to show the equation or you remember the equation? Hello? Yes, sir.
Yes, sir.
Can you hear me?
Yes, Professor.
Yes, sir. We can.
Yeah, you understood what am I asking you to do?
Sir, memorize the formula.
No, you wrote
Yeah,
the
take
write
it to
down. That is
paper.
why I told you to write down the formula. That will be useful. Right now.
Yes, yes, sir.
Yeah. Write down the formula I am giving you.
Right, sir.
I want you to work out. That is why I am giving you the formula. Please write it down.
Yes, sir. We are ready, sir. You can.
All of you have written? Now,
No, no, sir.
yeah, you have written, right?
Yes, sir. Yes, sir.
Now, for this state of stress, sigma 1 is equal to minus sigma, sigma 2 is equal to plus sigma. Plug that in. Sigma 3 is 0.
So square root of 3 sigma square is
Yeah, root 3 sigma.
root 3
Sorry?
sigma. Root 3 sigma.
Root 3 sigma is equal to
Sigma y.
sigma is equal to sigma y by root 3.
root 3. Yeah.
Yeah, I think it should be sigma y by root 3,
0.577.
not 2. It should have been root 3 then. Okay. Understood? That means when sigma is equal to sigma y by root 3, that is when failure happens. You don't need to. So, for example, if you are applying only uniaxial tension, the amount of stress that you will apply is up to sigma y. But if you have a biaxial loading in the other direction, if it is opposite load, then you will see that it is only sigma y by root 3. You don't need to apply sigma y. Is that clear?
Yes, sir.
Yeah.
Yes,
Yes,
sir.
sir.
Yeah. Now, consider the case. What is the third state?
Sigma 1,
Sigma
sigma
1
2
is equal to
equal to
sigma.
sigma
Sigma 2 is equal to sigma and sigma 3 is equal to 0.
0.
What do you get?
Root 2 sigma.
So now root 2.
Sorry?
Root 2
Sigma
sigma.
equal to sigma y by root 2.
Sigma is equal to sigma y by root 2.
Yeah. So here it should have been sigma y by root 2. Okay. It's not sigma y, it should have been sigma y by root 2. Then this one, sigma 1 is equal to sigma 2 is equal to sigma 3 is equal to sigma. All three are same.
For the third case, I'm getting sigma y actually.
Sorry?
For the third case, I'm getting sigma. Just the sigma. Sigma y.
Which one? Third case, huh?
Sigma is to sigma y, right?
Yeah,
Yeah, it is sigma y only.
it cannot be root 2 or.
Sigma is equal to sigma y you are getting, correct?
Yes. Third case.
Yes, sir.
Yeah, then it is correct. So whatever, whoever said y by root 2, that is wrong. So how about the last one?
So all will be minus sigma, sir, if I'm not wrong, right?
All
Sigma
are
1,
plus
sigma
sigma
2.
or minus sigma does not matter.
Doesn't matter.
Plus or
Yes,
minus.
yes. Right, sir. Right.
What do I get? What is the sigma value? At
Root
which?
6 sigma.
Huh?
Or sigma y by root 6.
Root 6, huh? That is not true. Sigma 1
So
square.
sigma y, we are getting 0.
0 times sigma is equal to sigma y. So sigma
Correct.
will become sigma y by 0. That is
infinity.
That means for this particular state, for it to plastically deform, you need to apply infinite stress. That is why yield strength will be infinite. Understood? It will never yield this particular thing. Okay. Because it is pure hydrostatic state of loading. All three directions are same. There will be only volume change. There won't be shape change. That is why it will never plastically deform. That is what distortion energy theory says. Now, whatever equivalent stress, that is square root of sigma 1 square plus sigma 2 square, now that we can see it as equivalent stress, can you calculate the equivalent stress for this state of stress and this state of stress? Please work out. When I say equivalent stress, I mean square root of sigma 1 square plus sigma 2 square plus sigma 3 square minus sigma 1 sigma 2 minus sigma 2 sigma 3 minus sigma 3 sigma 1. That quantity I want you to compute. For this state of stress and the second state of stress, because in the yesterday's class we have stopped here.
For the first one, I am getting 5, sir.
Second one.
Me too, sir.
Second one also 5, sir.
Hmm?
Second one is also 5.
So what is the meaning of this? First one also same equivalent stress. Second one also same equivalent stress. What is the meaning of this?
The deviatoric parts are same.
The deviatoric parts are same. If you look at the second stress, can you write the second state of stress as first state of stress plus 10, 0, 0, 0, 10, 0, 0, 0, 10.
Yes, sir.
But 10, 0, 0, 0, 10, 0, 0, 0, 10 is hydrostatic state of stress. Will that cause any distortion?
No, sir.
No. Since that part does not cause distortion, only although these two states of stress values are different, as far as plastic deformation is concerned, these two are exactly the same. That means they will yield at the same time, or they are at equidistance from yield point. Can you see that? Yesterday we thought this is actually closer to yielding, isn't it?
Yes, sir.
But now, after looking at the distortion energy theory, we realize that it is not anywhere closer to yielding than this. Both of them are equidistant from yielding. That means both of them are equally probable for yielding. Can you see that?
Yeah, yes, sir. Yeah.
Okay. So the concept of equivalent stress is very useful. Now what we have done in this distortion energy theory is that we have tried to derive a one-dimensional equivalent of a 3D state of stress and then compare that one-dimensional equivalent stress to the yield strength of the material to decide whether the material is failing or not. Okay? All right. So the statement of distortion energy theory is sigma y is equal to square root of this. So when this becomes equal, that is when failure happens. In 2D, if you are dealing with only two-dimensional problems, the maximum principal stress is sigma 1, minimum principal stress is sigma 3. It can be negative also. So sigma 3 and hence sigma 2 is equal to 0. That means one of the principal stresses is not there because it's a plane stress. Then this equation becomes sigma y is equal to square root of sigma 1 square plus sigma 3 square minus sigma 1 sigma 3. So sigma y is a material property. It is a constant. So you can write this guy as sigma 1 by sigma y whole square plus sigma 3 by sigma y whole square minus sigma 1 sigma 3 by sigma y square is equal to 1. Because if you do square on both sides. So that is an equation of an ellipse. And if you would plot this equation in sigma 1, sigma 3 plane, this is how the equation looks like. This is an ellipse. And all the points within this are less than sigma y. And any point outside this red region will give you sigma y greater than sigma y. Here sigma y is replaced with sy just to for some textbook it uses sy. So instead of plotting with respect to sigma 1 and sigma 3, I am normalizing with sigma 1 by sy and sigma 3 by sy. Then the ellipse looks like this. So that means this is what we call yield surface or yield locus. Any stress state within this ellipse will be set on this ellipse is actually plastically deforming. Is it clear or are there any questions here?
Clear, sir.
Clear. Okay. So distortion energy theory in 2D is an ellipse oriented at an angle 45 degrees to the principal axis. Okay. It is an ellipse in the principal stress space. And if you are plotting this guy in 3D, because it's for a 3D state of stress, that will be a cylinder, a circular cylinder, which is oriented at an angle 45 degrees to each of the sigma 1, sigma 2, sigma 3 axis. Okay. So all the stress states inside the cylinder are safe, or on the cylinder are plastically deforming. Okay. And when you are talking about 2D, you cut any plane, then that will be an ellipse like that. That is why on an ellipse, if you cut it an ellipse, then it will be, so it will look like a, if you cut this cylinder at a certain angle, because it's oriented at a 45 degree. Suppose if you are saying sigma 3 is equal to 0, you have to cut like this, then you will have an ellipse here, and that is what you are seeing here as an ellipse in sigma 1, sigma 3 plane. And which state of stress is likely to cause yielding? Because this can be written as this plus this, because this is hydrostatic part that does not cause any yielding. So this and this are equivalent as far as plastic deformation are concerned, that we have discussed already earlier. So this quantity is called von Mises equivalent stress. And when you have the stress state written in terms of principal stresses, you can directly use this formula. If the stress state is not written in principal space, but if it is written in some arbitrary plane with sigma xx, sigma yy, sigma zz, tau xy, tau yz, tau xz, then also you can directly compute the equivalent stress. Now we define an important quantity called factor of safety. Factor of safety of your design is given by the yield strength divided by the equivalent strength. Okay. So the modified distortion energy theory is, if you have some factor of safety, then the failure happens when equivalent stress is equal to sigma y by n. N is your factor of safety. Okay. Now, let us say this is the state of stress. Please note it down. 10 minus 6 0 minus 6 10 0 0 0 1. So for this state of stress, I would like you to compute the hydrostatic part and deviatoric part. It is written here, but I would like you to make sense out of it. So the total stress can be written as deviatoric part, that is S, hydrostatic part is sigma H. So hydrostatic part is sigma H is equal to sigma 1 plus sigma 2 plus sigma 3 by 3. Sigma 1 plus sigma 2 plus sigma 3 is an invariant quantity, trace. So that must be equal to 10 plus 10 plus 1, sigma xx plus sigma yy plus sigma zz. So sigma H, or the mean stress or hydrostatic stress, is called 10 plus 10 plus 1 by 3, that is 21 by 3, that is 7. Right? So your hydrostatic stress will be 700, 070, 007. And this is your total stress. So the deviatoric part will be 3 minus 60 minus 630 00 minus 6. Okay. And if you find the principal stresses of this state of stress, they are 16, 4 and 1. That means the eigenvalues of this tensor is 16, 4 and 1. Now you have this guy, which is a deviatoric stress tensor. The eigenvalues of this guy will be minus 6, minus 3 and 9. And you will realize that the trace of this deviatoric stress tensor will become 0. That is the first invariant. J1 is equal to 0. I1 means 10 plus 10 plus 1, that is the trace. I2 is sum of the principal minors. I3 is the determinant. Similarly, if you take a deviatoric stress tensor, the invariants of the deviatoric stress tensor can be either eigenvalues of the deviatoric stress tensor or trace, sum of the principal minors, or J3 is the determinant of the deviatoric stress tensor. Okay. So the invariants for deviatoric stress, the first invariant of a deviatoric stress tensor will always be 0. Okay. Now let us look at the state of stress. Let us solve this problem. Now I will not talk anything. I would like you to look at this boundary value problem and then tell me if the material is yielding or not. Look at the problem and try to solve it. I am not going to talk about it. You need to try. Are you able to work out? So first of all, write the stress tensor. Can you tell me what the stress tensor is?
200, 0, 0, 0, 130, 0,
Wait a
30,
minute.
50.
Wait. So first row is
200, 0, 0,
0, 0. And second row is
0, 130,
0, 100, 30. And then
0, 30, 50.
0, 30, 50. Everyone agrees with that?
Yes, sir.
Yes, sir.
What is the positive x direction? Positive z direction is in which direction?
So
I think
the
that is
ninth
minus 50.
component
Top to
minus
bottom.
50.
Minus 50 MPa.
Minus 50. How about tau yz? Is it positive or negative?
Even that should be negative. Sorry, that should be minus 30.
Minus 30, minus. Yeah. So if you make that mistake, you are going to get a different result. Be careful.
Correct. Yeah.
Now, how will you find the equivalent stress? So how do you go about process? So you have the stress state. Now you calculate the equivalent stress corresponding to the stress state and check whether that is equal to yield strength or not. Correct? So for finding the equivalent stress, this is the formula. Sigma x, sigma y, tau xy, tau yz. You can use this formula because you don't need to find sigma 1, sigma 2, sigma 3. You can directly use this formula. Have you written the formula?
Yes, sir. We written, sir.
Yeah. So now if you have written the formula, now let us go back to the problem.
So I'm
Sigma
getting
y.
173.
So you get sigma
Equivalent stress sigma E 173.
173 MPa. What is
Yeah,
the yield strength?
approx. It's 500.
So is it safe or not?
Yes, it is. It is not
Then
yielding.
what is the factor of safety? How do you define factor of safety? Sigma y by sigma e.
Yeah, that is 2.8.
2.8. But I got 224.
Yes, sir. I'm also getting 224.
I'm getting 218, sir. Means it's
How come each one of you can get different numbers? So your factor of safety will be 2.23. Is the formula wrong or? I'll give you correct formula only. So where did you go wrong?
Let me recalculate. So
Anyone got 224?
Yes, sir. I'm getting
Yes, sir.
224.
Yes, sir. Yes, sir. I'm getting
Divide by
224.
2
Okay.
is 4.
Yeah. So now let us do a scenario. We have made a mistake in two symbols. Let us make minus 50 to be plus 50. What happens? Let us see. Instead of writing sigma z is minus 50, we have written minus 50 to be plus 50. Then what is the equivalent stress?
Then 173.78.
Yeah. The previous person who got 173, he used that instead of minus 50, he used it plus 50. Then you have estimated a higher factor of safety, which is dangerous, right? When you do the design. Instead of minus 30, if you take plus 30, will it change anything?
No, sir.
No.
No, sir, because it's a square
No, sir.
Yeah.
It is a
actually, so not change.
So, right, so we have now sigma. Now what I want you to do is you got the total stress. I want you to write what is the hydrostatic part and what is the deviatoric part of the stress tensor. Sigma H and sigma D. Sigma H stress tensor is what? Sigma D stress tensor is what?
Sigma H is 250 by 3.
Yeah. So how do you write? 250 by
take
3,
sigma
0, 0, 0 250 by 3, 0, 0 250 by 3. That is your sigma H tensor. So sigma D will be sigma minus sigma H. Isn't it? Deviatoric stress tensor. So calculate the deviatoric stress tensor.
So 116.67 on the diagonal.
Sorry, what did it?
116.67.
What is that?
Derivative stress
No,
tensor.
divisory stress tensor I want.
Okay.
Is it 116.667, 0, 0, and then 0, 16.667 minus 30, then 0 minus 30 minus 133.333.
Yes, sir.
Yes,
How much
yes,
is it?
same.
Yes, sir. I was also saying the same.
First, what is the first value?
116.67.
One 16.7 minus 30, 0 minus 30, 133 minus 133.3. Is that correct?
Yes.
Yes,
Yes,
sir.
sir.
Hello?
Yes, sir. That
Yes,
is
sir.
Yes, sir,
Getting the
same.
same.
Yeah, good. So now, if you got the deviatoric stress tensor, can you find the second invariant of the deviatoric stress tensor? What is the second invariant of the deviatoric stress tensor?
Sum of the principal minus.
Can you do that?
So I'm getting some negative value, 16,738.
Good. So multiply that with so instead of taking sum of the principal minors, you take the negative of the sum of the principal minors. That means multiply it with -1. Call that as J2.
So is that I2 or J2?
J2. Call that as J2. I2 is for the full stress tensor. This is only for
Yeah, understood, sir. Thanks.
got it? So you look at this equation. The equivalent stress can also be written as square root of 3J2, where J2 is the negative of the sum of the principal minors of deviatoric stress tensor. So what we have calculated now is the sum of the principal minors. If you multiply that with -1, that becomes J2. And now your equivalent stress should be equal to square root of 3 times J2. Can you calculate this? Whether you are getting the same equivalent stress that you have computed earlier. Square root of 3 times 16733, whatever you got.
Yeah, 224.08.
Right? So
Yes, sir.
even if you don't remember this formula, you know how to compute deviatoric stress tensor given any stress tensor. From there, you can compute the second invariant of the deviatoric stress tensor, that is negative of the sum of the principal minors, and square root of 3J2 will give you the equivalent stress. And once you have the equivalent stress, you can compute the factor of safety. So you don't actually need to remember any formula. Is that clear?
Yes, sir, but the sign we need to change. Any
Yeah, so
specific
the
reason
definition
for
of
that?
J2 is not the sum of the principal minors. The definition of J2 is negative of the sum of the principal minors. Got it?
So
Okay,
that
sir. Yeah,
that means
got it, sir.
J2 will always be negative, right, na sir? If that
J2 will become positive if you don't multiply with the negative. The definition of J2 itself is negative of the sum of the principal minors.
exactly, sir. So, I got the point. So if I don't multiply with the negative term,
Mm.
so the principal, that means that will
Always,
always
yeah, you are right. The sum of the principal minors of
it will,
deviatoric stress tensor will always be a negative quantity.
oh, that's fine. Because that will also indicate whether the calculation is going right direction or not in that way.
Correct. Yeah.
Yeah.
Clear? Okay. Now let us look at the next failure theory, what we call maximum shear stress theory, which is also called Tresca-Guest theory. What this theory says is that the failure occurs when the maximum shear stress in a part exceeds the shear stress in a tensile test specimen. Okay. Suppose if you are doing uniaxial tension test. Okay. Let me use to explain it clearly. Let me use my iPad writing. So what it says, the maximum shear stress theory, when the maximum shear stress induced in the part or material exceeds the shear yield strength of the material.
Sir, all these theories are based on uniaxial tension test, no, sir.
Because we are measuring uniaxial tension test and hence we are trying to write the failure theory with respect to uniaxial tension test. Okay?
Great, sir. Thank you.
Yeah. Now, so this is a uniaxial tension test. Let us say I am doing a uniaxial tension test. The Mohr circle for uniaxial tension test will be this is sigma and that is tau. For uniaxial tension test, if this is my specimen, I am doing this is let us say sigma. So at the onset of yielding, this will become yield strength, right? That is when this applied stress becomes equal to sigma y, that is when failure takes place. That is when the plasticity deformation happens, isn't it? So corresponding to this stress state, the stress state will be sigma y 0, 0, 0, 0, 0, 0, 0, 0. Right? So sigma 1 is equal to sigma y at yielding, sigma 2 is equal to 0, sigma 3 is equal to 0. Right? So sigma, let us say this is my sigma y. Sigma 2 is equal to 0, sigma 3 is equal to 0. This is sigma 2 comma sigma 3. Now, how do you draw the Mohr circle? That is my Mohr circle, right? This is the Mohr circle for uniaxial tension test at the onset of yielding because the principal stress becomes equal to sigma y. Is this clear? Okay. Is this clear?
Yes, sir.
Yes, sir.
Yeah. Now, although you are applying uniaxial tension test, this is your maximum shear stress, but that maximum shear stress is yield at the onset of yielding. That is your shear yield strength, tau y, right? Or I would call ys, yield strength in shear. That will be equal to what? So tau ys is
Half of
equal
sigma
to
y.
sigma y by 2, isn't it? Because from here to here, sigma y, this radius, this is the center of the circle. This value is sigma y by 2, and hence this value will also be sigma y by 2. So the shear yield strength is sigma y by 2. All of you agree with this?
Yes, sir.
Yes, sir.
So this is my tau max, that is the maximum shear stress. So if I am applying a uniaxial tension test and if it is a shear yield strength, then the maximum shear stress induced is corresponding to the shear yield point, and that will be shear yield strength. That's the shear yield strength will be 1/2 of the normal yield strength. Okay. Now, what is the maximum shear stress? This theory says when the maximum shear stress induced in the material becomes equal to shear yield strength of the material, that is when failure happens. That is the maximum shear stress theory. Now, if your stress state is sigma 1, sigma 2, sigma 3, three principal stresses in that direction. That means sigma 1 is greater than sigma 2 is greater than sigma 3. Now, let me draw the Mohr circles for this. For a three-dimensional state of stress, okay, let us say sigma 1 is the largest, and let us say this is sigma 2, and that is sigma 3. Okay. Now the more circles that we need to draw are one between sigma 1 and sigma 3. This is sigma 1, sigma 3 Mohr circle. And the next Mohr circle that I would draw is between sigma 1 and sigma 2. And the next Mohr circle that I would draw is between sigma 2 and sigma 3. Okay. Now, among these three Mohr circles, what is the maximum shear stress? This is the maximum shear stress. Can you see that? Because
Yes,
this
sir.
is another shear stress, this is another shear stress, but maximum is this. That is tau max. In that case, tau max is equal to sigma 1 minus sigma 3 by 2. Do you agree?
Yes, sir.
In a full
Yes, sir.
3D state of stress, when sigma 1 greater than sigma 2 greater than sigma 3, the maximum shear stress is sigma 1 minus sigma 3 by 2. Agreed? So now what is the maximum shear stress theory saying? When my maximum shear stress becomes equal to shear yield strength of the material. Maximum shear stress is what? Sigma 1 minus sigma 3 by 2 becomes equal to shear yield strength is sigma y by 2. That implies, according to maximum shear stress theory, my failure happens when sigma 1 minus sigma 3 is equal to sigma y. That is the statement of maximum shear stress theory. Is that clear?
Yes, sir.
Yeah. So coming back to the slides. So that is precisely what I have described until now. Sigma y, shear yield strength is sigma y by 2. So the maximum shear stress, when it is equal to sigma y by 2, that is when failure happens. In a 3D state of stress, sigma tau max is when sigma 1 greater than sigma 2 greater than sigma 3. The maximum shear stress sigma 1 minus sigma 3 by 2. That is when the failure happens when sigma 1 minus sigma 3 is equal to sigma y. Or failure happens when sigma 1 minus sigma 3 is greater than sigma y. As long as sigma 1 minus sigma 3 is less than sigma y, the material is safe. Okay. So now, let us look at this scenario. So in sigma 1, sigma 3 plane, let us draw the failure surface or failure locus. The case 1, sigma 1 minus sigma 3 greater than sigma y, and let us say a scenario sigma 1 is greater than sigma 3 greater than 0. That means both sigma 1 and sigma 3 are positive. That means what? It is in this quadrant. Right? Both sigma 1 and sigma 3 are positive. Then the failure happens, whichever sigma 1, if both of them are positive, then in a 3D state of stress, sigma 2 will be 0, isn't it?
So can you repeat? Couldn't follow.
So what I am saying is, you have a 3-dimensional state of stress. In 3-dimensional state of stress, what we said was sigma 1 greater than sigma 2 greater than sigma 3. If that is the case, then maximum shear stress will be sigma 1 minus sigma 3 by 2. Correct? That means maximum principal stress minus minimum principal stress. Do you agree?
Yes, sir.
So that is what we need to do. So now let us keep this sigma 1 minus sigma 3 should be equal to sigma y is our relation. Now imagine a scenario now we are looking for plane state of stress in 2 dimensions. Let us develop the maximum shear stress theory in 2D. In 2D, let us say both sigma 1 and sigma 3 are greater than 0. Because it is a plane state of stress, what should be the value of sigma 2? Sigma 2 should be 0. One of the principal stresses have to be 0. No? If sigma 2 is 0, will the maximum shear stress in that case will be what? If sigma 2 is equal to 0. So let me plot it for you again. Let me again.
It should be sigma 1, right, sir? Because always sigma 3 should be 0. It should be considered as the minimum stress value.
So sigma 2 should be considered as the minimum stress value, and hence sigma 1 minus 0 should be equal to sigma y. Therefore, sigma 1 is equal to sigma y. So the failure line will become sigma 1 is equal to sigma y. That is the case 1. Okay. Case 2, when sigma 1 is less than 0. Because it is a plane state of stress, sigma 2 is equal to 0. In this scenario, sigma 1 is maximum principal stress, sigma 3 is the minimum principal stress, then no problem. So our original relation sigma 1 minus sigma 3 is equal to sigma y. Sigma 1 minus sigma 3 is equal to sigma y. Because sigma 1 is in positive and sigma 3 is negative, that the line will be this line. Sigma 1 minus sigma 3 is equal to sigma y. When sigma 1 is positive and sigma 3 is negative. And the third scenario, where both sigma 1 and sigma 3 are less than 0. Then sigma 2 will be 0. That means that will be the maximum principal stress and this will be the minimum principal stress. Then minus sigma 3 should be equal to sigma y. So that will be our case 3. So these are the 3 scenarios. Similarly, you can also generate a scenario where sigma 3 greater than 0, sigma 1 and vice versa, so that you can also generate these 3 lines. So eventually this is the boundary that we have generated with these cases. Similarly, you can generate 6 other cases by interchanging sigma 1 and sigma 3. Then you will get this line, that line and that line. So this enclosure, which is a hexagon oriented at an angle 45 degrees, is the locus of the maximum shear stress theory. And on the top of that, if you superpose von Mises theory, this is how the von Mises theory locus looks like. So now you only focus on the boundaries of these 2 theories. This is the maximum shear stress theory. This is the maximum shear stress theory. This is the red color is the von Mises theory, and this is maximum shear stress theory. Okay. Now you will see that when you are having uniaxial tension along sigma 1 or sigma 3 uniaxial compression, you will see that the maximum shear stress theory and distortion failure. Any other point, there will be a variation. So for example, if you look at this fellow, this point is same for maximum shear stress theory and distortion energy theory. So if your stress state is along that line, then both of them will give you same factor of safety. We will talk about it in the next class. A little bit more detail we will analyze, but for now you should realize that the failure surface in 2 dimensions for maximum shear stress theory is a hexagon, whereas for a maximum distortion energy theory is a von Mises theory. It is an ellipse oriented at an angle 45 degrees. Is that clear?
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Okay, so I think if that is clear, the 3D, in 3D, the maximum shear stress theory will be a hexagonal cylinder, a cylinder with a hexagonal cross section. Whereas for distortion energy theory, it's a cylinder with circular cross section. For maximum shear stress theory, it is a hexagon, a cylinder with a hexagonal cross section. That is the only difference.